Hello, there have been a number of videos that have come out by various debunkers asking flat earthers the question of the angle to Polaris and to explain why traveling along any given meridian that you would travel 69 miles for every degree of latitude. This would be true whether you're at the equator or whether you're at 45 degrees or approaching the North Pole. And one of the questions that was asked to flat earthers repeatedly was the angle to Polaris, and some of them even made challenges, such as Mr. Sensible. I'll put a card to Mr. Sensible's challenge video here and his response to Mitchell's response here. And it's not surprising at all that Mitchell kind of did not understand the challenge and essentially proved that the angle to Polaris is impossible if the Earth was flat. And I thought that I was going to do something similar myself in my own sort of way, so I even used the Theodolite app on my phone whenever I would go on some walks, thinking that I would end up using that to show the physical demonstration, as these flat earthers claim, how looking at streetlights get smaller as they get further away. And unfortunately, before I even got to make this video, Critical Think managed to beat me to it with his observations. I'll put a card to his video right about here as well. So I don't really feel the need to show my own physical real-world measurements and observations. So this video is strictly going to show the modeled observations that we can also confirm by taking our own measurements wherever we are. Just to recap what the problem is, if you are standing at a latitude of 0 degrees, and I've placed it on the prime meridian facing north, Polaris is just slightly off of an altitude of my latitude. And as I move towards the North Pole, as you can see here, the altitude to Polaris happens to match my latitude. We can also see what happens if we just look at the horizon. And what I've done is I've locked the altitude at 0 as I move towards the North Pole. All of the stars appear to shift up, and it's very quick before Polaris and the northern celestial pole move out of your field of view. And then at the very end, if you're standing at the North Pole, Polaris is straight up with an altitude of 90 degrees. The next thing that I wanted to do was to model what would happen if we are, let's say, on a causeway or on something with water on either side, and there are lamp posts on the side of this walkway or causeway or whatever. And as we approach, how would the streetlights appear to look when I'm focused entirely on the light in question? When we're in a city and we're looking at a bunch of streetlights, there are natural hills and depressions in the road. There are nearby buildings, and it becomes very apparent very quickly that you cannot see a streetlight many kilometers away. But because this is a model, I'm looking at the lampposts that are 5 kilometers away, all the way to where I'm underneath that first lamp. I'm also using trigonometry to calculate the altitude of the camera required to keep the first lamp in the middle of the screen, and I'm also computing the zoom level or the field of view in degrees to keep that lamp post at the same size regardless of how close or how far I am, and this would represent what we would see with our eyes. So as you can see, as I'm approaching, not only do I have to look up, but I also see that the object is getting larger. I have several other animations as well. I'm going along the same 5-kilometer route as before. The camera altitude remains the same as well. However, as I'm approaching now, I'm readjusting the zoom level so that that light stays the same size throughout the entire trip. Finally, my videos would not be complete without spreadsheets. We know by observation what the altitude of Polaris should be at any given latitude. And for context, the northern celestial pole represents a 90-degree declination and a 0-degree azimuth. The altitude to the northern celestial pole depends on your latitude. Polaris has a declination of 89.264109 degrees, and as Polaris rotates around the northern celestial pole, when it is at its highest in the sky, Polaris will appear to be at your latitude plus 0.735891 degrees, and when it appears at the lowest in the sky, it's going to be your latitude minus 0.735891. 6 hours after either of these, it will either appear to match your latitude, but it will be a positive azimuth from 0, or it will appear with an azimuth of less than 0. In my spreadsheet, I've matched it so that Polaris appears at its highest altitude, which would be right about here. At the equator, it would appear at 0.73589101 degrees. As we move towards the North Pole, you can see that the altitude to Polaris increases. You can also see that as we approach the North Pole, the distance in kilometers decreases and matches the equivalent of 69 miles per degree. If we come back to the problem of mapping the height to Polaris from our latitude, which is the challenge that Mr. Sensible had issued to Mitchell, if the Earth was flat, we would use standard planar trigonometry to calculate how far away from the North Pole we would be if we used the angle that was observed. One of the many things that we've asked flat earthers is what are the heights of the stars? What is the height of the sun? How high is the moon? We can only estimate how high it would be with an angle of 45 degrees. And if I am at 45 degrees and I am 5,004 kilometers away from the North Pole, that would mean that the height of Polaris would have to be 5,004 kilometers high. So if we assume that the height of Polaris is 5,004 kilometers and we have a measured angle to Polaris, that would mean that without accounting for any type of refraction, we would have to be at almost 400,000 kilometers away from the North Pole in order to see Polaris at that angle. If we know the distance from the equator to the North Pole and we know the height of Polaris, we can calculate the expected angle up to Polaris, which would be 27 degrees. In this column, I calculate the difference between the two. What I've also done was I've used the same trigonometry functions to calculate what the expected height of Polaris would be above the North Pole if we knew the distance to the North Pole and we knew the observed altitude or the angle above our horizontal reference line. And as you can see that if I can see Polaris with an angle of 0.735891001 degrees above my horizontal reference line, that would mean that Polaris would have to be 128 kilometers above the North Pole. As I approach, you can see that Polaris is moving further and further away from the surface of the ground. When I finally reach an observed angle of around 45 degrees, it would be at the expected 5,000 degrees above the surface of the ground. And finally, as I approach the North Pole, Polaris should appear to be well over 100,000 kilometers above my head. And as you can see, not one of these numbers are anywhere near consistent. So once again, flat earthers keep saying perspective is the explanation, when perspective does not match any math at all and does not match the observations that we make. So now I'm going to play those animations that I've shown already so that you can get a good look at them. And that's going to be it for this one. If you liked it, you know what to do. If you didn't like it, you know what to do. Thank you for watching, and I'm going to see you again in another video, hopefully soon enough. So bye for now.